Welcome to Lecture 20, Properties of Power Series. To motivate this, let's consider the following example. So here, for any value of x, and now x is going to be a variable, the following expression is actually a geometric series. Recall by a geometric series, I mean successive powers of something. Typically, we've taken a constant r and we've looked at successive powers of r. But here I'm going to say, let's let x be a variable. It's unknown. This is still a geometric series. Our constant a is equal to 1. And now r, the thing that we're taking powers of, is a variable x. So this series converges. This is something we already know. If the absolute value, or the norm of r, which in this case is x, is less than 1, or equivalently, if x is between 0 and, or is between -1 and +1. So on the real line, so here's -1 and here's +1, this series is going to converge no matter what value, or say it this way, as long as our variable x is in this interval. So as a preview, we're going to be calling this the interval of convergence. So this chapter is, you can think of this as a generalization of a geometric series where we're allowing our r's to be variables, and then we're going to ask for which values of x does this series converge. And in this example, the answer is for this interval right here. Okay. So as a definition, let x be a variable and let a be some constant. Then this series, this expression right here, just successive powers of now x minus a, is called a power series centered at a. A special case of this, probably the most common, the one we'll see most often, is this guy, which is a power series centered at 0. This can be convenient up here because sometimes, let's take this power series and let's shift it to the right. Let me get my pen back here. Suppose I were to take this power series. Suppose this is a function and we could graph it. I don't know. Suppose it's something like this, and we wanted to shift it to the right by that's supposed to be a purely horizontal shift by a. So what's the difference between this series and this series? It's replacing every instance of x with x minus a. And so that's, if this series is represented by this power series, or this function is represented by this power series, then shifting it to the right like this is just this thing here. So we don't lose any generality by letting a be non-zero, but it's usually convenient to just consider the case when a equals 0. And that's probably the most common case as well. So here's one technicality that I need to get out of the way before we continue. So consider a power series. You look at this and you should think these are just successive powers of x minus a. So the right hand, so this thing, if you were to multiply it out, looks something like this, right? Well, I have a quick question for you. What happens if you plug in x equals a? Now, if you do this, let's do this right here, n equals 0 to infinity, you have, so we have cn times 0 to the n, right? And so what's that first term? The first term is c naught 0 to the 0, and 0 to the 0 is not defined. So let's continue. Let's ignore that for a moment. Keep going. C1 times 0 plus C2 times 0 squared plus etc. Now, we don't have any problems with these terms being 0. But what we want, if you look at the right-hand side of this equation, when you plug in x equals a, all of these terms go away, and we're left with just this guy here. So we want this to be equal to 1, although we can't really make the case that 0 to the 0 is equal to 1. Now this would be evidence for it. So so to get around this, we actually have to define, so let me get my pen back here. So if x equals a, then how do I want to say this? How about when n equals 0, c naught times 0 to the 0 is the series. I maybe could have said that a little bit better. And this is undefined. So the solution to this is we actually want to define x minus a to the 0 to be equal to 1 for all x. So if we do this, every power series converges, just think, is defined at its center. So if we didn't actually make this definition into technicality, then the series would technically not be a well-defined function at the center at point x equals a. So we're going to get around this. Maybe it sounds like cheating, but trust me, it's not. By just defining the series, or by defining x minus a to the 0 to be 1 for all values of x, even when x is equal to a. So now that we've got that really insignificant technicality out of the way, the main question I want to ask, which is something I alluded to on the first slide, is for a given power series, when does it converge? So for example, before I go over this theorem, let me do the example we did before. I said x to the, so n equals 0 to infinity. This is 1 plus x plus n plus x cubed, etc. And here you can really see why I want, to do the definition I did before, where 0 to the 0 is equal to 1. Because usually what happens is we start out with something like this, and we want to write this in a nice closed form expression, and here's how to do it. Except the n equals 0 case is technically wrong, so we just get around it by defining it. Okay, so this power series, it converges on this interval meaning that for all points x in here, so if x is between 1 and -1, this series is going to converge. So we want to ask this in general. Now, is it possible that there is a power series centered at 0 that converges for all negative numbers but not positive numbers? Or is it possible for it to converge for two disjoint intervals, or for a closed interval where the endpoints are included? Is it possible for it to converge for some sort of asymmetric interval from like -1 to 2? The answer to all of these are no. So there's actually only 3 possibilities. So one possibility is the series converges only at its center A. So for any power series centered at A, I don't care how bad this is, if you plug in x equals A, then the series, as we've defined it to be, just C naught. That will converge. So every series converges at least in the center. Another possibility is the series converges absolutely for all x. It doesn't matter what you plug in, you're going to get some function. And the third possibility is that the series converges absolutely, but not everywhere. So this is the case we've seen before, over an interval centered at A. This is the example down here. A is equal to 0, and the series converges over this interval. And so mathematically, that just means converges for all points a distance less than r from the center. So in this case, A equals 0 and R equals 1. So this is our center, and R, this is called the radius of convergence. So every point within a radius big R of the center, the power series is going to converge. So a related concept, let me write this down. Hope I have enough room. So a related concept is, so I've just defined the radius of convergence, but a related concept is the interval of convergence. And hopefully, I'm not going to define it, hopefully you can see what it is. It is, instead of just saying, well, here's an interval centered at A with a radius 1, instead of just saying those 2 points, I could instead just specify what this interval is. So in this, and I'm going to call this interval of convergence, I'm going to call this IC. So in this case, instead of specifying A and R, I could have said the interval of convergence is -1 to +1. So let's go back to these 3 cases and see what the interval of convergence is. So in case 1, the interval of convergence has radius 0. So it's how do I want to say this? I guess I could say this as, oh, that's, let me erase that. So one way I could express that is as this closed interval, or if you want to, I could just say it's a single point A. So if the series converges only at its center, then the interval of convergence is just a single point. If the series converges everywhere, then the radius of convergence is infinite. It's the entire real line. So I could say it's -infinity to +infinity. And finally, the last case, the interval of convergence is going to be A minus R and A plus R. Okay, so next what we'll see, I'll show you, given a power series, how to find the interval of convergence. And we'll usually do this by doing the ratio test. Okay, so here's an explicit example. Here's a power series. And let's find the interval of convergence. So given this abstract sum, let's figure out what values of x we can plug into here and actually get a number. So notice that this series, I'm just going to take a moment to write it as n equals 1 to infinity. How do I want to do this? This is, let's pull out the n and the 4 to the n plus 1. And then let's write this as x minus -1 to the n. And so from here you can see that a equals -1. So this is a power series centered at -1. So what we know is that the interval of convergence is going to look something like this. We just don't know quite how big this is going to be. It could be the entire real line. It could also be only the point -1. Okay, so let's apply the ratio test. So with a ratio test, the limit as n goes to infinity of a to the n plus 1 over an. So remember, the series is going to converge when this limit is less than 1. So let's figure out when this limit is less than 1. And this will be an expression in terms of x. Okay, so this limit is the limit. I'm going to omit the n goes to infinity because I think that should be clear. So at the limit, let's be careful here. Okay, so the n plus 1 term is n plus 1. Let's do that first. let's do x plus 1 to the n plus 1. And let me do, how do I want to arrange this? Let me do divided by 4 to the n plus 2. That's the top. And the bottom is going to be, that's easier, n times x plus 1 to the n over 4 to the n plus 1. Okay, so let's simplify that. Okay, what do we have? So this thing here that I'm circling in red, that will simplify to x plus 1, right? Yeah. So it's x plus 1 to the n plus 1 over x plus 1 to the n, so that's just x plus 1. This thing here, let's be careful with this. This is 1 over 4 to the n plus 2 divided by 1 over 4 to the n plus 1. So that is invert and multiply, so it's 4 to the n plus 1 over 4 to the n plus 2. That's equal to 1/4. Okay, good. So this is the limit on the top of, okay, x plus 1 is on the top. We also have an n minus 1, or n plus 1. And on the bottom, we have a 4, and we have an n. Okay, great. Okay, actually now I lied. I'm going to keep the n goes to infinity because we have several things, and we've got to be careful as to what we can pull out of this limit and what we can't. And the x plus 1, even though x is a variable, we can pull that out because we're only, you can pull out anything that's a constant with respect to n. So this really can be pulled out, and so can the 4. So I'm going to write this as x plus 1 over 4. I should actually say absolute value of x plus 1 over 4 times the limit as n goes to infinity of what's left. There's an n plus 1 at the top and n on the bottom, and I can actually omit the absolute value sign here because those are going to be positive. Notice that this limit is of course equal to 1. So this whole thing is equal to the absolute value of x plus 1 all over 4. Okay, so what does this tell us? So the series converges if and only if, that's double F means if and only if, this limit that we got by the ratio test, this thing has to be less than 1. That's what the ratio test says. So now we just have an algebra problem involving inequalities. So this is x plus 1, absolute value of x plus 1. That should be that. Let me erase that and make it more legible. Absolute value of x plus 1 has to be less than 4. That's the same thing as saying x plus 1 has to be less than 4 but greater than negative 4. And now we can add, or we can subtract negative 1 from all three sides and get negative 5 is less than x is less than 3. Now if you had the reaction that, ooh, some of this inequality stuff, you're rusty on it, so am I. I think honestly this is the lowest, the easiest stuff in the whole class, but it's the stuff that makes me think twice more than it's the stuff that I am the shakiest on, is going from here to here. And it's silly because this is like an 8th or 9th grade thing, but that's the thing that I always have to think twice about. Okay, so what this tells us is that the interval of convergence, so let me circle this in red. So this is values of x for which the series converges. So this means that the interval of convergence is this interval right here. So let me circle that as double box that. So going back up to the top, let me put a -5 right there and a +3 here. So this is the interval of convergence. So the interval is centered at -1, and the radius of the interval is r equals 4. That's the radius of convergence. Okay, so to summarize, we had a theorem that said there are 3 cases. One of them is the radius of convergence equals 0, which means the interval of convergence is just a point A. Second case is that the radius of convergence is infinite, which means that in other words, the interval of convergence is the entire real line, -infinity to +infinity. And the third case is that there is some finite radius of convergence. And this was the case in this series, this example that we just did. Our series was centered at -1, and our theorem told us that for all values of x in this interval, the series converged. So technically, and it's a small technicality, we haven't actually determined whether or not the series converges at the endpoints. So it's easy to do. Let's just check. Let's check to verify that the series, in fact, does not converge at the endpoints. So let me say that. So let's check endpoints. Because all we have for the theorem is that we know that all these blue points, all these values of x inside this open interval, the series converges. We don't know yes or no about the endpoints. So let's check the 2 endpoints. Let's do x equals -5 first. So here, what we're going to do is we're just going to plug in -5 into here and see what we get. So we plug in n equals 1 to infinity of n -5 plus 1 to the n over 4 to the n plus 1. So this is n times, that should be an n, times -4 to the n over 4 to the n plus 1. Now we can factor out this -1 to the n and write it as -1 to the n times n over 4. And let's factor out the 4. This is 1/4. N equals 1 to infinity. -1 to the n times n. So does this converge? So this, well, by the divergence test, this thing does not go to 0. I mean, what is that? That's an alternating. So that's just an increasing sequence of numbers alternating in sign. So let's write. How do I want to say this? So this series diverges by the divergence test. Okay, so we know that the series does not converge at this endpoint, and we'll show similarly that it's not going to converge at that endpoint as well. Let's do that quickly. So x equals +3. So let's plug in x equals 3. Let's see what we get. We get n times 3 plus 1 to the n over 4 to the n we get pretty much the same thing, except it's positive n times 4 to the n over 4 to the n plus 1. And so, well, now I'm just going to skip to the last step. Now we have 1/4 times n equals 1 up to infinity of, what do we have now? Yeah, we just have n. And this thing also clearly does not go to 0. And so, therefore, this entire sum diverges by the divergence test. So we do conclude that in this case, our interval of convergence is in fact. I'm not going to say this happens for every single time. Honestly, I don't remember offhand if there is an example where the interval of convergence includes one of the endpoints. I'm not actually sure if there is. I tend to think there's not, but in this case we have verified indeed that the interval of convergence is equal to the open interval from -5 to +3.